Here we go. It's Monaco here again. Your boot camp is well underway. We're at the turning point of your podcasts. Number 4, measurement techniques. So we're going to go over reading measurement tools and accuracy. And you're going to have another Google Classroom assignment for homework credit at the end of this particular lecture cast. Okay, so let's get into it. Estimating the last digit in measurements is something we need to learn how to do in science classes. Rulers, many are familiar with that. You're using them in your shop classes. They measure length. Duh. Graduated cylinders, you've all used these before. They measure volume. And digital balances measure mass. The important thing to remember is when you're reading a graduated cylinder, there's a right way to do it from the bottom of the meniscus. That's the curve there. Boom, that star, that's where you read your graduated cylinder. And make sure your eyes are level with the water. Crouch down and keep your graduated cylinder on the table and look level through the water to make your reading. A volume by displacement is very simple to do, but you have to remember that you cut the initial volume out of the final volume to figure out how big the volume of the object was. Okay, so here's an example. Graduated cylinder has 16.5 mils of water in it. The marble is added to the water and the volume rises to 22.4. You might be thinking, duh, of course it's going to go up. But what is the volume of the marble? Well, you got to do a quick subtraction. So initial volume, 16.5 mils. The final is 22.4 mils. So you're going to take the final minus the initial to find the volume of the object. So I'll just do 22.4 minus 16.5. Longhand math here. Oh, 5.9. 5.9 milliliters is how big that particular marble is. Okay. And that's volume by displacement. Very simple, very straightforward. Got to know how to do it backwards, forwards, left, and right. Mass. Mass of a solid object is very simple. You put it on the scale. Make sure the scale says 0 first, but then you put your solid object on it, and then you read the mass. Indirectly massing is very important for doing things like powders. Okay? You tear the 0 and then records a mass of a container. So if I have to measure a powder out, which you will do this year, you have to put the powder into something. Well, that container has a mass in itself, so you have to 0 the balance on the container. It's really important to record the mass of that container as well, just in case something goes wrong with the balance. You can backtrack and figure out mathematically how big your sample actually was. Subtract the mass of the container from the container in the sample. It's kind of like the volume by displacement, except you're going to subtract what the container weighed out, which was the initial mass. So here's an example. Weighing dish, like our container, is placed on a digital balance. It has a mass of 93.4 grams. That's how much the dish weighs, so we'll write that down. The powdered chemical is added to the dish and the final mass is recorded as 105.7. So the dish plus the powder weighed 105.7 grams. How much does the powder weigh by itself? Well, you do a subtraction by difference. 105.7 minus 93.4. And you just do your math like that. 7 minus 4 is 3. 5 minus 3 is 2. 10 minus 9 is 1. 12.3 grams is the mass of the powder. So that's mass by difference. Very similar to volume by displacement. Simple enough. Okay. Accuracy and precision. This is where we talk about estimating the last digit in our measurements. The closeness to a desired value is your accuracy. So it's like hitting the bullseye when you're aiming for it on the target. Okay, how consistently you can do that is your precision. So anybody can get lucky and hit the bullseye even with your eyes closed. But if you can hit the bullseye every single time, you're not only accurate, but you're also precise. So if you look at these 4 kids down here shooting darts, pellets, or whatever you want to think about it. Cheryl, Cynthia, Carmen, Cassie. Maybe this is the strike zone. Baseball season's coming to an end. Cheryl looks like a pretty bad pitcher. Cynthia's pretty consistent and not so bad. Carmen looks like she's right on the money with the strike zone. And Cassie is consistent, but she needs some adjustment in order to be over the strike zone. So who's accurate, who's precise, and who is accurate and precise? I want you to try your hand at those, remembering that precision and accuracy are different things. Closeness to the desired value, accuracy, meaning how close did you get to the center of the target, and precision, how repeatable your results are. So you answer those three questions on the side yourselves in your notes. I'm not showing you the answers. Estimation. Whenever you estimate the last digit in a measurement, it creates error. That's human error or systematic error, and it's fine. You just have to call it out. You might be slightly wrong in chemistry class, but as long as you're only slightly wrong, you're still right, if that makes any sense. Every measurement has error, and we in chemistry class, we just call it out. Okay? So human error is associated with the person doing the measuring. How good am I using my ruler, my balance, my graduated cylinder? Maybe I'm really sloppy. That would be human error. Instrument error, on the other hand, is the error built into the instrument from the value that is read. So this is literally the estimating the last digit. Rulers only have so many lines on them. If your measurement falls between two lines, there's a plus or minus in that instrument. Okay? So instruments have built-in error. The more expensive the instrument, the smaller that built-in error is. A percent error is a calculation. So we're going to take our measured value, what we read to be the length of the block, the volume of the marble, the mass of the powder, whatever it might be. We're going to take away from it what we should have gotten and divide it by what we should have gotten and multiply by 100 to turn it into a percent. So the measure is what you got when you measure. The accepted is what you should get if you measured it correctly. And so a percent error sample problem. Okay. Student in the lab measures the mass of a sugar in a can of Coke to be 39 grams. So there's your measured value is 39 grams. They look up the ingredients and find out that it's actually 40 grams. What was the percent error? So if your measured value is 39 and your accepted value you should have gotten 40, you're a little bit off. How off are you? That's the percent error calculation. Now set it up. I want to see what your answer is. So percent error, measured value minus accepted. So we're going to do 39.0 minus 40.0 divided by 40.0 and multiply the answer times 100. Okay, make sure you do your subtraction in parentheses first, because PEMDAS, your math skills there, you got to do your subtraction first before you do your division and multiplication in order for your answer to come out with the right sign. I want to see what your answer is. Okay? That's how you do a percent error calculation. We're going to do a few of them this year. They're pretty straightforward. To wrap up this lecture, this notes, make sure you've taken notes on page 11 through 13 in your boot camp packet. Make sure you complete your Google Classroom portion of comprehension questions. And come to Class Compare to go over 3 pages in the boot camp packet of practice problems related to this concept and idea. Well, that's all, folks. Thanks for watching.